we've explored the gravitational force in some detail, and there's another fundamental force whose force equation looks very much like this, and it's the electric force. The electric force involves charges, not masses. And so the electric force an equation for the electric force has to capture the fact that we know that there are two kinds of charged particles. And we know that there's, if you have something like protons to protons, then they actually repel each other. The forces drive them apart. And if you have two electrons, the forces, they also repel each other, so the forces are. But if you had an electron and a proton, what you get is attraction. So an equation for the electric force has to fall out in the mathematics. And it turns out to be reasonably straightforward to do this by just assigning a plus or minus sign to the charge of these particles very conveniently. So we say that things like protons have positive charges. And things like electrons have negative charges. And presumably there's going to be two charges here in the force equation. So and the symbol Q is usually used to represent the charge of an object. So we're probably going to have a Q1 times a Q2. And in this case, we'd have some positive number times some positive number, so this would come out positive. And here we'd have some negative number times some negative number, so it would still come out positive. But in this case, we'd have a positive number times a negative number, and so the result would be negative. So if we, as usual, we know that for a vector, changing the sign flips the direction of the vector. So it would be consistent with both of those forces, repulsive forces being in the same direction, but this being in the opposite direction. So that's how the mathematics works out. The charge of a proton. So Q is a variable representing charge. The charge of a proton is a constant whose symbol we run out of letters in the alphabet all the time. So unfortunately, the symbol is plus little e, and its value in SI units is 1.6 times 10 to the negative 19 coulombs, which is the SI unit of charge. And the charge of an electron is negative E, so that's negative 1.6 times 10 to the negative 19 coulombs. And so the electric force has a lot of the same properties as the gravitational force. It also drops off very fast as two charged particles get farther away from each other. In fact, it's what's called another of these 1 over r squared forces, the same dependence. If you double the distance, the force goes down by a factor of 4. And it depends on the charges. And so, in fact, we could expect it to have a very similar form, and it does. So here's the electric force on object 2 by object 1. It's going to have the charge of object 1, which is not necessarily this number, but it is going to be a multiple of this number, because we don't have a way to, we've never found a way to split electrons in half or to have half a proton. So it's going to be this or twice that or 3 times that, or we might have to add up some things. So the charge of one object times the charge of the other object, we have this 1 over distance squared again, where r is as usual. So if we call this 1 and that's 2, then our vector r, we want the force, so that's r, that's r hat. So there's going to be an r hat here. There's of course a constant, and the constant in this case is a little more complicated in the way it's written than we may be used to. The constant is, it's a composite constant. There's a primitive constant epsilon 0, but the constant that goes in here is 1 over 4 pi epsilon 0, and the whole thing has the value 9 times 10 to the 9th Newton meters squared per Coulomb squared. Very similar. G has units of Newton meters squared per kilogram squared. So we have a 1 over 4 pi epsilon 0 here. And the reason it's written this way and not just as some K is that there are way too many things called K anyway. We have spring stiffnesses that are K, and you'll find there's a Boltzmann constant called K. But also because epsilon 0 has this life of its own, it turns out to appear in lots of important equations for electricity and magnetism. And so then the question is, in the gravitational force, we needed this minus sign to get the force in the correct direction, because if we had an r hat, we needed the force to be that way, so we needed a minus r hat. And it turns out we don't need that minus sign here, because in this case, we want the force on proton 2 by 1. So here's the vector r. Here's the vector r hat. We want it to be, the force needs to be in the same direction as r hat in this case, and it will be because both q1 and q2 are positive. So that comes out right. In this case, same vector r, same vector r hat. Again, we want this force to be in the same direction as r hat, and it will be because both q1 and q2 are negative, and you multiply two negative numbers, you get a positive number. And now in this case, so here's our vector r, here's our vector r hat. The force on 2 is opposite to r hat, and that's going to fall out because this is positive and that's negative, so this thing will have a negative sign, and so we don't need an extra minus sign here. And so let's see if we can squeeze this in somewhere. We'll erase the gravitational force and write the electric force up here. So we have this constant 1 over 4 pi epsilon 0, and the whole thing is equal to this 9 times 10 to the 9th, which means that epsilon 0 is something like 8.5 times 10 to the minus 12th or something. It's in the back of your textbook. Times the charge of object 1 times the charge of object 2 over the magnitude of r squared times r hat, with the same definitions of r and r hat. So both attractive and repulsive forces just fall out of this equation fairly naturally. And and that's useful. Now, it's interesting to do a calculation that gives us a sense of the strength of the electric force compared to something like the gravitational force. So let's consider a situation where we've got let's say we've got a proton and an electron, and they are a distance of a nanometer apart. So I think is what I worked. Yeah. So we'll make it. So this is a nanometer. That's 1 times 10 to the negative 9 meters. And the question we want to ask is, well, they have charge, but they also have mass. So they're going to attract each other electrically, but they're also going to attract each other gravitationally. In fact, we can make it more dramatic by making it 2 protons. So they'll repel each other electrically, they'll attract each other gravitationally. Let's do that. And so the question is, which force is bigger, the electric force or the gravitational force? So let's calculate the electric force let's calculate it on this proton here. We'll call this one 2. So that's going to be the vector r hat. So the electric force on proton 2 is going to be 9 times 10 to the 9th Newton meters squared per Coulomb squared times Q2 times Q1. So we have 1.6 times 10 to the negative 19 coulombs times 1.6 times 10 to the negative 19 coulombs divided by 1 times 10 to the negative 9 meters squared. And in this case, r hat is the vector by inspection. We can just look at this picture and see what r hat is, right? It's going straight up, so it must be 0, 1, 0. And so if we work this out, I think what we get, so this is about 10 to the 10th, and this is going to be 10 to the negative 18th, so we have 10 to the 8th, add a couple 10 to the negative 19ths here. So when I worked it out, I got 2.3 times 10 to the negative 10 newtons in the direction 0, 1, 0. I'm going to leave it this way because we're kind of interested in magnitude, comparing magnitudes here. You might do the calculation, make sure that you think I did it right. That doesn't sound like a very big force, although protons are pretty small. Let's find out the gravitational force that on proton 2. So that's going to be 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. And the mass of a proton is about 1.7 times 10 to the negative 27 kilograms. And again, we've got the same thing in the denominator. And so the electric force went up. We better have a minus sign here because the gravitational force is pulling them together. So this is going to be so we multiply this all out, and we get a number something like 1.9 times 10 to the negative 46 newtons in the 0, negative 1, 0 direction. Now that's really a much smaller force. In fact, if we take the ratio of the forces, we find something like the magnitude of the electric force between these two particles and the magnitude of the gravitational force, we get something like 1 times 10 to the 36th. So the electric force is much, much, much stronger inherently than the gravitational force. In fact, if you work it out, you'll find that the electric force is going to be stronger than the force the whole Earth could exert on that other proton, too. So this is a strong force. Well, I better not use this word. It's not the strong force; it's the electric force, but it's a substantive force that has a big effect. Let's think about this other aspect of the forces that we saw with gravitational forces here. So what's an alpha particle? An alpha particle is actually the nucleus of a helium atom that's lost its electrons. They're emitted, it's one of the common modes of radioactive decay for a large nucleus to emit alpha particles. So it's a particle that consists of 2 neutrons, which don't have any charge at all, and 2 protons. So its charge is plus 2e. So basically we've got 2 protons and 2 neutrons, and its charge is plus 2e. So 2 times 1.6 times 10 to the minus 19 coulombs. So we've got an alpha particle here and a proton here, and they're interacting electrically. And the question is, which of them exerts a force that's larger in magnitude on the other one? So the question is, what can we say about the magnitudes of these electric forces? The force on the proton is equal to the force on the alpha. The force on the proton by the alpha particle is equal to, larger than, smaller than the force by the alpha particle on the proton. Okay, so 80% say that these two forces are equal in magnitude, and you're right. And you're right, we can tell from the form of the equation that you're right, because the only thing that's different when we're calculating the force on the proton due to the alpha particle, or the force on the alpha particle due to the proton, we've got the charge of the alpha particle, we've got the charge of the proton. R hat is different, but R hat is a unit vector, and its magnitude is 1. Now, how does it manage to do this? How does this puny little proton manage to exert just as big a force on this big macho alpha particle as the alpha particle exerts on the proton? In this case, it's actually sort of easy to see. The proton, so here's some distance, and I've obviously exaggerated the size here, so basically all these things are exactly the same distance away. The proton exerts a force on this proton, and it exerts a force on that proton. So the net force is the sum of those two things. It's going to be F net. Here, this proton exerts a force on this proton. That proton exerts a force. And when we add them up, we get the same net force. So reciprocity is also a property of the electric force, just like it was for the gravitational force. This is sometimes called Newton's third law, but it's actually more revealing to think of it as a property of the particular forces. You can see it come out of the force laws. There are some forces, as I mentioned, where this isn't true, like magnetic forces. So it's more revealing to talk about it here. And it turns out that, as we'll start exploring in Chapter 4, when we start exploring contact forces that are made up of the interaction of lots and lots of protons and electrons, this reciprocity property still applies.